So as I mentioned before, in general, if you can, you always want to set up the experiment so that only the rate coefficient that you care about, that reaction is dominant. And you're sensitive only to that rate coefficient. And that makes the entire analysis so simple. It makes your experiment very directly connected to the parameter you're trying to determine. And it's great. However, oftentimes you can't figure out how to do it. And so then you're stuck doing these crazy stuff, like just cook stuff and see what you make. That's like Dr. Tsai did. This guy's Walker. Now, this is where, if you're really clever, even with a horribly complicated mixture, you can still make it interpretable. But you have to be really clever. So actually, I guess it's the practical advice. If you want to do this, find somebody who's an expert in this kind of chemical cleverness and go do a postdoc with them. And then you'll learn how to do it. So there's like ways you can add two species together and measure the ratio of the products you make and therefore infer a ratio of two rate coefficients by the competitive methods. You can do things where you switch the isotopes. So you feed something with a certain isotope label and then suddenly switch it to a different isotope label at the steady state condition and see how long it takes the isotope to come out in a different product. And you can infer things. So there's a lot of things you can infer from very indirect experiments, but you need to be clever to set up an experiment like that to make it so it's going to be interpretable, what you get. And then even then, sometimes the interpretation is a little bit ambiguous because you have to make a bunch of assumptions about what's happening in order to get it. So anyway, if you want to read some brilliantly done ones, these Walker papers are just fantastic for doing experiments that if you look at it, you're like, what the heck? It's a horrible mess. Zillions of things are reacting. And then somehow he's able to get firm conclusions out of it by just very cleverly making little changes to the system and adding, and then doing very careful interpretations of it. All right. So now I'm going to switch, and we're going to start talking a lot about hydrogen and oxygen chemistry. And I'll talk a little bit more about the motivation later, but the main motivation here is that in flames, in premixed flames, the main thing that's happening is that heat and H atoms are diffusing into the unburned fuel and air mixture. And they're making reactions. Most important in this reaction, H plus O2, which we're going to talk about in some detail, happen in the premixed, and they're warming up the unburned premixed mixture. And the chemistry that's happening there is super crucial for how fast the flame is going to propagate. Because that's really what's driving, the fact that that chemistry is happening just sort of upstream of the flame is the critical thing that's making the flame move upstream. But to understand this, you have to think about hydrogen and oxygen chemistry, and it's super complicated. So this is if you have different hydrogen-oxygen mixtures, and you have different temperatures of the mixtures and different pressures, at some conditions, if you put a spark in there, you'll get an explosion. At some conditions, it'll just burn quietly, or maybe not even burn. And so then they even have these different limits for whether or not you get explosions as you change like the pressure. It's like not obvious at all why this is, but it's revealing the complicated chemistry that's happening underneath. So what's happening is that this reaction, H plus O2 to OH plus O, this is like the most important reaction. And some people even call it, this is the combustion reaction. And this is the reaction that makes the radicals in a high temperature system. So if you have an H atom comes in, it makes an OH, so one radical to one radical, but the O atom is actually a diradical. It's a triplet with two unpaired electrons. And it'll react further and actually make two radicals. So altogether, this had one radical come in, and it makes three radicals on the right side. So this is a radical amplifier. You have some concentration of radicals. It gives you positive feedback to make more radicals. And so this is super important. It's just like if you hold a microphone up in front of a loudspeaker, you hear this, all of a sudden you get this huge shriek. And that's because of the feedback that the signal's going in the microphone, it goes out the loudspeaker, the sound wave goes into the microphone, it amplifies. And if there's positive feedback, very quickly, things explode, things go crazy. And that's the same thing happening here. If you get a situation where this has positive feedback, one radical in makes 3 radicals out, they come back around and make radicals, and it goes around and around and around. And each time you're making more and more and more radicals. And the radicals are also catalyzing all the other reactions in the system, right? Because the radical plus stable is the main chemistry. So the heat release is also increasing as the radicals increase. That makes the temperature higher, which makes all the rate coefficients higher. So everything gets faster, faster, faster like that. And it goes, once you get to the point where you have positive net feedback in the whole system, then a microsecond later you have an explosion and basically you go to equilibrium because you just make infinite amount of radicals, infinite amount of heat. The temperature goes like crazy. And you basically run until you run out of fuel and oxygen. Basically it all gets consumed and you reach your equilibrium state. So this is the key thing that's happening. And this is what's causing these explosions. But this H plus O2 reaction that makes all these radicals is competing with other processes. So at the first limit, at very low pressures, the H atoms can diffuse a long distance, and in a normal sized reactor, they can diffuse all the way to the wall and then react with the steel in the wall and disappear from your gas phase system. And so that process is competing with the H reactor with the O2 at very low pressures. You have very little oxygen. So as the pressure increases, you have more oxygen, the more likely you'll react this way, and then you'll get into positive feedback. So as you increase the pressure from very low pressures, then you'll hit an explosion limit where this will explode because the H plus O2 takes off. But then as you increase the pressure higher, there's this other reaction, H plus O2 also, but now plus a collision partner to make HO2. And this is one of these reactions that's reversible and limited by the heat loss. So this reaction, here's HO2, here's H plus O2. This is a barrierless reaction. It goes in and forms HO2. But when these guys react, the energy is conserved. So you form HO2 in this very high energy state. So this is like HO2 that's vibrating like mad. And it has energy above the dissociation limit. And the main thing it does is you form it, and it just falls right apart, back to H plus O2. So the reaction is like 0 at low pressure. And it only reacts, this reaction only is effective because you have collision. Something else, M, collides and takes away some of the energy that's vibrationally excited HO2 and makes it HO2 that's down in the well, is trapped. And now you've net run the reaction. And this is rate limiting at low pressures. So that's what you see here, is that if you're low pressure, that reaction is negligible. This H plus O2 plus M is negligible. But as the pressure gets higher, 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 eventually that reaction starts to be very important. And what it does is it takes away your H atoms and makes them HO2, which is a very unreactive species. So it's sequestering your H's. It's hiding them and making them not available to do the important reaction. This is the important reaction that gives the positive feedback. So this turns down the gain of your positive feedback amplifier until you turn the gain down so much there's no positive feedback anymore. And all the H atoms just go away. So then you get nothing. No reaction, there's no explosion. All you do is you're doing a slow oxidation to make HO2. The HO2s mostly kill themselves off by radical recombination reactions. And so you just get a slow peroxidation of the hydrogen. Yeah?
So I know I missed it, but is the complex the same for both reactions? Is it both HO2, the double dagger?
Yeah, yeah. This is a pretty weird situation. That the important reaction also goes through the same complex, and up higher is OH plus O. And so if you come in, these guys have a Boltzmann population. If you come in the very tail of this population, you'll be high enough that you come in, you form HO2 very violently vibrating like crazy. It's vibrating so hard it can break the OO bond and make OH plus O. And so at the high temperature, this is what's happening, and this is the important reaction. It's endothermic too. So only the very, very high Boltzmann tail. But there's a lot of, all the rest of the H plus O2s could do this thing. However, at low pressures, they can't do it because they do it and immediately comes back. And it's only when there's high enough pressure to trap them, then that basically will wipe out all the H atoms. All the H atoms will get trapped and converted to HO2 at high enough pressure. So pretty interesting for just 3 atoms. They're doing a lot of chemistry. Question? Yep.
Does the shape of your container have significant effect?
Yeah, so people have done that, and also the wall material too. So if you change the material, you change down in this very low pressure limit. You change the shape, like the surface to volume ratio or how far you are. You change the material in the wall. Some materials, H atoms stick to it really well, and sometimes they bounce off. And there's a whole literature about this. And actually, in safety engineering, they even have specifications about what the surface to volume ratios have to be, stuff like that, in order to make sure that the wall's like helping with a safety thing. Yeah. And actually, some people recently have started to use this as a beneficial experimental thing where they do reactions to little capillary tubes, and they use the wall reaction intentionally. Whereas most kineticists think the wall reaction is confusing, and they try to use really big tubes to get the walls far away from your reactants. So anyway, there's a whole literature about this. I don't know too much about it, but I see papers once in a while. People are talking about this. And then if you go to high enough pressure, you have another reaction that H2O2 can collide with a gas and get heated up to make two OHs. And that reaction is actually endothermic, so that's mostly at the higher temperature end. And part of this is that in addition to losing radicals to the wall, if you're running exothermic reactions, you're also losing heat to the wall. So you initially have a mixture that's isothermal, the gas and the wall all the same temperature. But as you start to oxidize the hydrogen, you're releasing heat. If the container's big enough, the heat that you generate in the center might not get to the wall very well, so the temperature in the center of the reactor could be different than the wall temperature. And it might be hot enough, might get hot enough that H2O2 decomposition happens and makes OHs, and the OHs can attack the hydrogen and make more heat, and you actually get an explosion starting from the center of the mix. So anyway, this is whatever size chamber you have, you get a shape like this, but the actual shape will depend on the wall material and the surface to volume ratio, the geometry of your reactor, and the pressure. So this is pretty confusing, and this kind of stuff, when people first started doing combustion, we're like, what? Everybody did a different experiment. They thought they were doing the same experiment, and they would get completely different results. In a big way, it's like, do I have an explosion that's going to kill somebody, or do I just have some slow oxidation, right? It's like a pretty different result. So people have studied this a lot, and they really know the reactions for H2O2, and you can figure out you're sensitive mostly to this one reaction, H plus O2. But these other guys, like H plus O2 plus M, show up. And then actually even this other thing, this is O2 plus H2 reacting to make 2 radicals. So the reverse, when you start, you have no radicals in the system. You need to make some. The very first thing happens is O2 attacks the H2. It makes HO2 plus H. Later, if you run it enough, you have a lot of H and HO2, and they can the reaction can run the other direction. So that's another thing to have. That reaction is quite slow, though. Once you get enough radicals, it's totally negligible. All right, so this reaction is super important. And in a regular fuel, you don't have hydrogen, right? You have hydrocarbon, maybe. And the key question is, when I make the radicals, do the radicals make an H atom or not? Right, I'm making H plus O2. It's going to make some radicals. And the key question is, like when an O atom reacts to the fuel, it's going to make some fuel radical. Is the fuel radical going to break up to make some number of hydrogen atoms? And if it does, if it makes enough hydrogen atoms, these hydrogen atoms will come back and react with oxygen again and make more radicals. And if net, I'm making radicals when I go around this whole cycle, then I'm going to have a positive feedback. I'm going to have an explosion. And if net, the number of radicals is decreasing. Like I put 7 H's in, and when I come back around, if I only have 6 H's, then the reaction is going to die off. I perturb the system by putting some radicals in, and actually it's stable. It won't do anything. But if it amplifies, it'll be unstable, and it'll explode. And so this is why we have explosions, right? I mean, so you want to watch a Hollywood movie? Things are blowing up. It's because they can get this reaction running where you make more H atoms than you feed. And if you can do that, then you get positive feedback, then you're going to have an explosion. And that's basically what the Hollywood guys doing special effects, they count on this. to make this work. Okay, so now we're trying to think about premixed flames. In premixed flames, suppose you have a condition where you can make positive feedback. Then if I can have a little bit of H atoms diffuse into the fuel air mixture that's at that condition, that has the right fuel and the right temperature, the right pressure, so that I can get positive feedback, then those little bit of H's that diffuse upstream from the flame are going to form a whole bunch more H atoms there. And the reactions start going, and basically it'll look to you like the flame moved from the left to the right into the mixture. What happened really was that a little bit of H's and T's, a little bit of temperature moved upstream, a little bit of H atoms moved upstream, and they started the reaction there. And the reaction moved. It's not like all the stuff in the flame actually moved there. Does that make sense? So the flame speeds are actually faster than the diffusion rate of some of the species in the flame. It's due to the fact that the H atoms have a high diffusivity because they're light, and then the heat conduction usually is faster than the mass diffusivity. And so the flame looks to you, your eyeball, like it's moving, but actually the atoms, the carbon atoms you're seeing, aren't moving nearly as fast as what you're observing. And then exactly how sharp that front is controlled by how strong this amplification is. So this amplification is really strong. So the moment a little bit of H's get there, you get a lot of H's. Then those H's themselves will diffuse upstream. And you'll keep on maintaining a high gradient of H concentration because I keep on making so many H's. If you don't keep making them fast, the gradient drops, right? The gradient will drop because they're diffusing away all the time. They're diffusing faster, the sharper the gradient is. So the diffusion is trying to kill the gradient, and it's got to be the chemistry has to make the gradient by making them faster. So depending on how strong this is, that will control how good how fast the flame front is. Because the diffusion is driving the flame front, diffusion of heat and of H atoms. All right. So here's the picture again I showed you before of how inhomogeneous the situation is, that in less than a millimeter, you're doing these huge changes, and you get these really sharp gradients, both of temperature and of the concentrations of the species. And it's not shown on this plot, but we showed before that the equilibrium concentration of OH is like not much less than CO, right? It's up here. So somewhere in this range is also OH, which is a radical, and then down a couple orders of magnitude is the H atoms, which are the ones that really matter the most. But the OH is actually matters too. The problem is the OH diffuses slower, so it's not as important for the flame speed. All right. So the simple analysis of this, and how many of you are taking Professor Madelon's class? Okay, so he's probably talked about this already, has he? Yeah, so the flame speed depends on the square root of diffusivities and square root of chemistry somehow, roughly. It turns out that a lot of fuels turn out to have very similar flame speeds because they have similar adiabatic flame temperatures and similar thermal diffusivities. So the heat fluxes are pretty similar. There's some things that there's some compensation things that the diffusional losses of H and T increase, so it sort of tends to make things all more or less the same. There's a few odd cases. So hydrogen has a much higher flame speed because every time a radical reacts with hydrogen, it always makes an H atom. Whereas other fuels, it's like maybe half the time you make an H atom. So you end up having much better feedback because it always makes H atoms. So you basically get a feedback factor of 3. Every time you go through that cycle, you get amplification factor of 3. Whereas a normal fuel, you might get amplification of 1.5 or 2. And then the H2 itself is fast, so it also is diffusing. And that it can kind of diffuses towards the hot flame. And then acetylene is very odd too. And I think this is because acetylene has a much higher reactivity of O atoms than anything else. So O atoms actually have barriers for reactions with almost everything. It's a relatively unreactive radical. But O atoms plus acetylene has a very low barrier and very rapidly makes H atoms. So that's unusual. All right, so this is what's known about this. If you do a sensitivity analysis of a lot of conditions, you'll find the most sensitive reaction is H plus O2. So this is the one rate coefficient you really need to know if you're going to try to accurately predict combustion. And because of that, a lot of people try to measure it. And recent measurements, this is from 2011 from the Stanford group with the shock tubes, they're able to get down to 10%. This is really good. So this is quite hard to be sure you have a rate coefficient of 10%. You have to make sure you have a very uniform temperature. You have to know what the temperature is very, very accurately. And it's just hard to do. You have to know, how much oxygen you have, better than 10%. So that's also even just that can be hard. But they've done it. And so now there's a good agreement about lots and lots of measurements to get a tight number in that rate coefficient. But we're so sensitive to it that actually, even with 10% error, this is often the dominant source of uncertainty in a prediction, is this 10% error. People have tried to measure the reverse reaction and then use the thermochemistry to infer the forward reaction. And so you can react an O with an OH and make these products. And this would be at lower temperatures. At high temperatures, you want to run the other way. Low temperature, you run this way. And typically, this would be done with flow methods. And so this is a way to double check how good it is. But you can see the accuracy is not as good. So this is a log plot, log. So this is a log plot, it's still pretty good scatter in a log plot. So that means it's pretty big errors. So compared to the Hong determination, this is not as good. But it does more or less agree. So at least we feel like it's definitely an elementary step. And we know the thermo of H, OH, O, and H2, O2 well enough that we can do this. So when you make the OH, everybody knows what OH does. It reacts and it hits the fuel. It pulls it and it makes water. But for the O atoms, people don't know what it does so much. And so there's been some attempt to try to do this. So here's the O plus H2 reaction. And how they tried to measure this is back in the 80s. So they did it this is a flash photolysis experiment. And then people have also done it by shock tube. So different methods. These comparisons of different methods is actually pretty good for identifying the systematic errors associated with the different experimental methods, because they should all get the same number, but in fact they don't. So then people went back and looked, and they found out that shock tubes, the real temperature tends to be a little bit higher than what they think it is. But in other methods, usually the real temperature is a little bit lower than what you think it is. And they failed to figure out corrections for all this kind of heat losses and reasons why the temperature changes. And then this is the competing reaction, the collision. We showed that, so H plus O2 plus M. This one is very important and a little problematic because there's not very good spectroscopic ways to measure HO2. So you can measure the disappearance of H, but H plus O2, it could be going to OH plus O, or it could be going to here, and you don't know which one it is. This is not so easy to figure out. What they found out, one thing is that this reaction, you can write it as third order all the time. That means that it's so pressure dependent that at the highest pressures they can achieve, it's still linear it's still limited by the heat transfer, by the collisional energy transfer. That's the limiting step, even at really super high pressures. They've done flash photolysis for many, many different cases and found out that the H2O has a really high rate. So if you use H2O as the collider, you get really different rates than you do for any other collider. And so people speculate that there's some kind of hydrogen bonding between the HO2 that's formed and the H2O, and somehow that does something that makes it really good at collisional energy transfer. But I would say this is a still unresolved problem about why H2O is 100 times more effective at quenching this reaction than all the other partners. This is a problem in your kinetic models because in any case where you're running the reaction H plus O2, you're also making steam as a coproduct. And so at different locations in your flame, you have really different amounts of steam. And the steam, if the steam is the dominant quencher, then you have a really different positive feedback initially that's getting quenched as you're making more steam as a colliding partner. And so you get some really strange nonlinear dynamics that affects the flame speed and stuff like that. So this is a technical problem if you're trying to really get good precision of your model to the experiment. Yeah?
So out of curiosity, let's say you mentioned a little while back that metals had the wrong thermodynamics.
Yeah.
Doesn't the active thermochemical tables, isn't that supposed to kind of handle it?
Well,
Because it needs to be
yeah, so the problem right now is the active thermochemical tables, as implemented in the public version, only does enthalpy and doesn't do heat capacity. And the error in methyl was in the heat capacity. So, yeah. Sorry, the question was, doesn't the active thermochemical tables handle problems like the fact that we had the methyl thermo is wrong? So the methyl thermo, the way it's believed to be wrong is that the heat capacities, the high temperatures are incorrect because they were computed with some assumptions that aren't valid. So you would think that active thermochemical tables should automatically fix everything. But it turns out that as implemented right now, it doesn't fix stuff to do with heat capacity because they just didn't write it in the code because they thought we knew the heat capacities. So they just wrote it as you type it in, that's it. And that's not the way it is. So they're changing the code now to have it reflect corrections, and heat capacities will also correct everything. But so far not.
And out of curiosity, so if the reaction with H plus O2 goes to OH is the most important reaction, why don't people invest a lot of time and effort on theoretically coming up with
They have, this is like, yeah, so there's, in the last decade, probably 100 papers on both theory and experiment on this reaction. It's by far the most studied reaction. But the problem, and they have it to 10%. 10%, that's really good. But it's still not good enough for this one because it's so sensitive. So even though you have much better, tighter error bar on this rate coefficient than you do in any other rate coefficient, it's still not good enough. And so people spend a lot of time to worry about it. All right, here's some of the data on this reaction. And you get an idea of how big the error bars are. So, this is what the experimentalist error bars are. This is somebody tried to fit it as a function of temperature. First of all, you see it's not Arrhenius, because if it was Arrhenius, you'd have a straight line fit, but it's not. So there's an issue here, like what functional form should we be fitting it to? And then you can see the data are not internally consistent all the time, that there's an error bar. This data is not the same as that data, right? Different people measure stuff. And there's like, nothing's perfect in this life, right? You try your best. You get the numbers you can. You get the error bars that you think are the truth. But then you can see, probably this guy's error bar, maybe his error bar is bigger because, the data, it looks like the trend line is up here. Who knows, right? Maybe the trend line's wrong. Maybe it really should be curved like this, right? There's a lot of reasons why this could be wrong. And so, there's a gross of papers and conference discussions about exactly this. And, the theoretician says, you're completely wrong down here. What are you having measuring such a low rate? And then the experimentalist saying, what do you mean? We both measured the same number. What's wrong with your stupid theory? Right? And so you have this kind of useful discussion. But, if you look at this, like the rate versus collision partner in the different partners, I mean, these are nice straight lines, so it really is third order. But they're different. The slopes are different. So this was kind of surprising to people that how, if you change the collision partner, the rate really changes a lot. And how it scales, it was a little surprising too. Like, it looks like helium and argon are really similar. But I think people thought that helium and argon actually are very different in collisions with molecules. So there's a whole big discussion about collisional energy transfer, why certain collisional partners are better at taking away the heat, taking away the energy than other ones are. And that's like very active. And there's papers published in Science about this. It's like a big topic of field research right now. All right. This, people try to measure it directly at high pressure. I'm sorry, the color. This guy, Ravi Fernandez, he made a really high pressure reactor up to 950 bar to measure this reaction to try to find the high pressure limit, because all the experiments never saw it go to the high pressure limit. You think at some pressure, the cooling should be so fast that you should be limited by the reaction, H plus O2, but the reaction part, how fast these guys can come together, should become limiting at some point, not the cooling. But nobody ever sees it. They always see the cooling as limiting. And so he tried to go to 950 bar and make the measurements. And so he did it. He photolyzed ammonia to make the H atoms. And then he did a HO2 spectroscopy where he detected the HO2 in the UV. And he actually can finally see that the plots become curved. So here's his data. And this is a log plot of pressure. And when you get the pressure really high, you can see this starts to curve. It's not a straight line. It was a straight line, at low pressures, but at high pressure it starts to curve over. And it should eventually, according to theory, become an asymptote at high enough pressures. You should no longer be limited by the cooling rate, and it should just be by the reaction rate. But nobody's really seen it there. I mean, his points, you can see it's curving, but it's definitely not reached the flat part yet. That's what he's using. I wouldn't do it this way, but that's what he did. So he photolyzed with 193. 193 is a mess because it photolyzes everything. Yeah. So I agree with you. This experiment is problematic. On the other hand, I don't have an apparatus to go to 960 bar. So he did it. He has the apparatus. I can't tell him he's wrong, right? Yeah. Since then, he's moved on to a new job. What's kind of cool, this is kind of cool, is you can make what's called a reduced order plot where you can take all the different collision partners and all the different data and put them all on one plot together. And what you do is you divide by the high pressure limit value, the asymptote. You measure the low pressure limit rate, what people measure in the region where it's perfectly linear. That gives you this thing K naught. And then you measure the actual K when you measure up to higher pressures where the thing starts to curve. And if you plot it this way, K, both divided by K infinity in a log plot, at low pressures it's a straight line. And then you see the curve. And this is with all different temperatures. And also these are with all different bath gases. And everything all collapses onto one curve. So this is like a way to make sort of dimensionless or something for kinetics. And so this shows that everybody's data is actually is all consistent. All the data on many, many different temperatures, many, many different bath gases. The truth is the truth. This is the truth. Why it's that way, how we would calculate it a priori to get it that way, I don't know. But experimentally, it's all internally consistent. So none of the experimentalists are wrong. They all did it right. And so this is pretty good, I guess. And then from this curve, the shape of it, they extrapolated up to figure out what this asymptotic value was, which would be, actually the way they plotted it, this has got to be 1, but that really sets what this K infinity is, the denominator there. All right, and so there was an evaluation done in 2012, this is a pressure-dependent reaction, so you have to, it's of this type, right? It's H plus O2 goes to HO2 excited, which collides and gets cooled down. And you think at the simplest theory, you'd expect if you did an analysis, a steady state analysis on AB star on the excited species, you would get this formula for what the effective rate should be. That makes sense. The reverse reaction comes in. And you could rewrite it this way. So this all makes sense. And this is called the Lindemann-Hinchelwood formula. It's from a long time ago. But the real system is more complicated because there's not just one AB excited. There's actually excited at different energy levels, all have different rates because they fall apart at different rates. And they get cooled differently. The ones that are high energy need more collisions to get cooled than the ones at low energy. And because of that, this formula is not actually right. It's sort of roughly right. But the right formula is this one, divided by Jürgen Troa. And this is the form that you should use, where you get this F factor. So it looks like the Hinchelwood form with this correction. And here's where the correction should be. And this is the formula for all these correction factors. Kind of a mess. But if you do it, it actually fits the data really well. And here's the theoretical derivation of why it should look this way. So then you have a few parameters that you determined from the Troa. And it turns out you can fit it this way. And anyway, read his papers if you want to do this. if you use ChemCan and Cantera, they expect this form if you have a reaction like this. And those parameters are all known now for so these guys, this paper by Burke, it gives you all the TROA parameters for H plus O2 plus M, error bars on them, everything about it. All right. I mentioned that this is another reaction that's really important. This one was confusing people a long time because it has this weird Arrhenius behavior at high temperature and then not anti-Arrhenius behavior at low temperature. And a lot of dispute about this one. And there's like a hole here where there wasn't any data at this temperature region, so people just drew curves. But what shape curve should you use? What's going on? I think nobody knows. The theory is that this part, at low temperature, what's happening is that HO2s can make hydrogen bonds with each other, and they make like a hydrogen bonding complex, and that makes it like attractive to get together. But that attraction is not important at high temperatures because the thing's not stable and will just fall apart if you make the complex. So that's the theory about why this goes up. But the data is not that great. You can see it's scattered. So this is still under some topic of discussion. And then this one was also measured very carefully by TROA. And here's the plotted data for that. And this is just straight versus the helium concentration. Look how many orders of magnitude they went. This is 6 orders of magnitude. No, 1, 2, 3, 4, 5, 6 orders of magnitude in pressure. They had a very, very fancy pressure cell that could do over 6 orders of magnitude. Again, I can't reproduce these experiments. I can't complain about their data. But they spent a lot of effort to try to really do this. But this thing is a second order reaction in radicals to OHs, so you have to determine the absolute OH concentration. But they did it by measuring the OH spectroscopically, but the spectroscopic bands widen due to pressure broadening at high pressures. And when you go over 6 orders of magnitude, that's a very significant effect. So then they had to make the spectroscopy at all the different pressures, figure out what the spectroscopic parameters were. This is like a nightmare. So this is like a tour de force paper to figure out this very carefully to measure this reaction over this huge range. And even then, you look at it, it's like, I don't know if it really matches the data or not, the curve. And anyway, this is another one that's still sort of under some discussion. And then people measure in reverse. You start with H2O2. You can do shock tubes at high temperature. And Hung, same guy who did the H plus O2, also did the dissociation of H2O2. And it's just beautiful. At high temperatures, they really understand this very well. But again, this is always in the extreme low pressure limit in these experiments. All right, up to 11. I guess we'll go a little bit further, and then we'll take a break. Yeah.
So how is one supposed to, what determines a collision is going to be exciting one or a de-exciting one?
Okay, so this is a good question. So the question is, what determines if a collision is going to be exciting or de-exciting a molecule? And the answer is, you have a lot of collisions, and they have a random distribution about whether they excite or de-excite the molecule. And there's, in order that the equilibrium distribution is a Boltzmann distribution, there's a certain ratio of the probabilities of de-exciting and exciting so that overall, when all the collisions happen, eventually you'll get to a Boltzmann distribution. So, but like the A factor, the probability of having a collision that changes a certain amount of energy, that is not known, but the ratio of whether it knocks the energy up or knocks it down, they have to be in a certain ratio in order to satisfy the thermodynamics. So we know that, and so it's if your bath gas is cooler than your molecule, then most of the collisions will deactivate because you're mostly going towards thermal equilibrium, which would bring the temperatures together, but you still have a certain percentage which will be the other way around, and vice versa. If your bath gas is hot, your molecule is cold. Like in the shock tubes, they heat the argon by the shock, but the molecule is slower to heat up, the big molecule, because it needs a lot of collisions to get heated up. But the argon, just one collision is probably enough to get the argons to fly around fast. So the argons get hot first, and then they have to heat up the H2O2 up to the temperature, and that's what you're measuring. And there's a pretty good theory for this, semi-good. A lot of constraints on what must be true about this collision process are known, and there's a lot of things, but the exact rate of exactly how much energy is going to be transferred is not known, and there's only been one paper, as far as I know, that tries to compute this from first principles. It was in Science last year, 2 years ago. Aaron Jasper was the first author, where he did a first principle calculation of the collisions and figured out exactly what's the probability. It's really hard to get it just right. It depends a lot on the inner wall of the collision. So like a bath gas comes in and bashes into your molecule. It's got to bash it hard enough that it's going to excite a vibration of the molecule. And that's pretty hard because the vibrational quanta are large. So there's only like high energy collisions that really smash into the molecule and squish the bond to make it vibrate are the only ones that matter. But those ones are hitting the repulsive wall between the two stable molecules. You have a stable molecule, they repel with a really strong force when they get mushed together. The exact shape of that repulsion is super important for this. And it's hard to calculate that accurately because it's a topic that in the past nobody cared. They knew it was repulsive, who cares? Now they really have to think, are we really calculating the repulsion really precisely or not? And then you have to average over all the possible angles of impact between the two guys. So that's also another confusing thing. All right, I'm going to briefly talk about computational kinetics. Maybe we should just take a break now. Let's take a break now, and then I'll start this whole topic. So let's be back here 11:15, so just about 10 minutes. Let's take a short break.